about doping? Or like doping?
Maybe.
Because erythropoietin is what like Lance Armstrong got in trouble for.
Yeah.
Because
is the OP thing?
EPO thing,
yeah.
EPO?
Yeah, because
yeah, that's the
EPO is a hormone that's in your body. So when you take it, you can't necessarily say like you're drugging because it's a naturally occurring substance. So they can't really test for that. Maybe elevated levels, but you could just be training really hard and you're producing more red blood cells. But you can look at, that's probably what he's talking about, like the development. If you have like crazy amount of reticulocytes, that means this process is being amped up quite a bit. So like the percentage of reticulocyte, like immature red blood cell over mature blood cell would be a lot higher, but usually it's at a kind of constant ratio because you're constantly recycling red blood cells and creating new ones. So that ratio should be about the same. But if all of a sudden you have like a ton of immature ones and then kind of this many mature ones, that means like your body is like going through crazy hematopoiesis and creating red blood cells. And so that's how you could tell that somebody was doping.
Okay.
Basically, I think that's what he's kind of talking about.
Yeah.
I don't know about the nucleus thing, or you might see a lot of these nuclei in the blood. Does that make sense? Because of this process, like you might see a lot of these, and you'll see a lot of just nuclei floating around, right?
Okay, maybe that's what he said.
Yeah, maybe something like that. So, but it's a good question though. So when your heart beats, you could think of like your whole circulatory system as one big connected tube, right? I mean, it branches and everything like that. And so one thing about resistance is if you increase the length of the tube, you increase resistance, right? Think of it like this, like if you had a straw filled with water, you could like blow it out, right? But let's say you had like a fire hose that's 20 feet long and it's full of water and you're trying to blow the water through. It's gonna be like way harder to blow like that much fluid through that long of a tube, even though you're blowing water through both. Does that kind of make sense?
So resistance is increased if it's dilated?
No, that's kind of an example. Like, or let's say you connected like 1,000 straws together, so diameter's the same, and that was full of water. If you tried to blow the water through it, it would be more difficult than if it were just one straw. Because technically the opposite is true. If you increase diameter, you decrease resistance. So, or pressure, right? So peripheral resistance is basically from your heart, what is the resistance to the rest of the body, pushing the blood to the rest of the body, okay? And because your body can control the length in a couple of ways, right? Because you have like capillaries, right? They kind of form these networks like this where the oxygen is delivered. And these capillaries kind of branch to each other like that to kind of connect and increase blood flow, right? But what your body can do is they're called precapillary sphincters, right? And so your body can basically kink this one, kink this one, kink this one, and kink this one. So there's only one pathway for the blood to go through the capillary. And that would decrease resistance, right? Because we're taking the length and like cutting it down so that there's only one way to flow. And resistance and pressure is a little bit different. So this may increase pressure, but it wouldn't increase resistance. Okay. For example, like if you are outside in the heat, your body's going to want to bring all the blood to the surface to dissipate that heat, right? So it's opening all these up so that your blood kind of flows to the surface and maximizes the blood in the capillaries to dissipate heat, right? But what that causes is your stroke volume to go down because your heart is technically working against more resistance. That kind of makes sense? And that concept is called cardiac drift.
So the more blood flow you need to the body or to specific areas, the more resistance there is to those areas.
Yeah, because your body is basically opening up all these pathways and essentially making that tube longer, even though it has branches and stuff, if you're making it longer, you're increasing resistance.
Okay.
And that's what I think he means by peripheral resistance. Did you
I
pull
think
up?
so, too.
Let's see.
What was
Okay. Yeah, so peripheral resistance is length times
that?
viscosity, right? Yeah, so you could think of resistance as length times viscosity over radius to the fourth, right? So this is the length, right? So this is what we're talking about. If you increase the length, you're going to increase this number, right? If you increase the numerator, it also increases this, right? In viscosity, if the amount of water in the blood gets really low, your blood becomes thicker, it becomes harder for the blood to pass through, right?
Mhm.
And then you have radius, and this is what we're talking about with dilation, right? And so as the diameter goes up or it becomes more dilated, resistance goes down because it's in the denominator, right? Because whenever you're looking at these fractions or whatever, you can just think if the top numbers go up, the end result goes up. If the bottom number goes up, the other one goes down, and vice versa. If this were to go down, resistance will go up. Can I make sense? But you can see, because this is to the fourth power, it has a really big influence, right? So at each increment that it dilates, it's to the fourth power impact on the resistance, right?
So can you think of resistance as equals how hard the heart has to work to get more blood to those areas?
Yeah, it's basically the force that your heart is working against to pass blood through the body. So yeah, kind of, and I don't want to say it's exactly one or the other because there's other influences in blood flow and pressure and stuff, but that's basically it. So, but this is the quickest way your body regulates peripheral resistance, one of the quickest ways, either through this or this, right? Because all of your vessels are lined with smooth muscle, right? And through innervation, your body can basically be like, dilate and all your vessels will open up, and that would drop resistance like immediately, right?
Mhm.
Or increase resistance. But the thing is, your body also needs to maintain pressures too. So if you're like exercising and stuff, you're gonna need more blood pressure to get oxygen to the tissues. So you're gonna vasoconstrict, right? So this is gonna go down.
Resistance goes up.
Resistance goes up, even though you're wanting to get more blood to the tissues, but it's for a different reason. You know what I mean? That's why I want to say, like, it's always depends on what the heart is doing again. I don't know. It's kind of like you usually don't have to think of it as a big picture like that necessarily. It's like these components. And so you'll have more blood resistance, but what your body can do to overcome that is cause your heart to beat faster. It'll secrete epinephrine to cause your heart to contract more forcefully to compensate for that loss in stroke volume. So it'll compensate. It's not like one or the other. We have to do this, so screw everything else. It's kind of like it'll do this because that's what's most demanding, and the negative effects of this, your body will make different adjustments to adjust for that.